Okay, let me get this set up live. Yes.
Have you ever heard about tickling the dragon?
Yes. Yeah, so it's been used to describe two different things, and one of them the term was actually used for, and then another they co-opted the term later. But there was a reactor at the INL that you had to do some process that they dubbed tickling the dragon's tail. And then later, after that expression came from that reactor, they applied it to the process Slotin used for separating the demon core, the one that caused 2 criticality accidents. Yeah. We'll cover that accident when we start talking about crit safety in this class. Glass. I'm not familiar with that accident. There's a really famous accident where they would take a screwdriver and put it between 2 hemispheres of reflecting material that was around a critical mass of plutonium. And essentially you lowered the top of the hemisphere. Show you a picture. So I don't know if you guys online could hear, but Michael's asking about tickling the dragon's tail, which was this accident. Louis Slotin used to hold these hemispheres apart with his thumb, and then he put the screwdriver in and lower this and hold it from going fully critical with that screwdriver. So just enough neutrons could leak out when all these hemispheres were on here that it wouldn't go critical. And the story goes that somebody surprised him. They like dropped a coffee cup and the noise made him jump and he pulled the screwdriver out and it went instantly prompt critical. And because he was standing so close to it, but between it and the other scientists in the room, and he reached down with his hand to pull it apart, he died and he saved everyone else in the room. No, he died.
When was this?
This was during the Manhattan Project.
Oh, okay.
No, he died slowly and miserably over several weeks, and he refused any medical treatment so people could observe, because he was one of the first people to die from a criticality. And dying after a criticality accident, that kind of radiation exposure, is terrible. The water in your body turns to acid. You have gastrointestinal syndrome, so you can't actually pass any material. It just sort of is this gross, constant waste inside of you that you can't get out. Your eyes bleed. He had beta burns all over his hand, so his hand was just a black stump from the beta radiation. It's terrible.
Did he take any pain medication, or was it just like no treatment, like to try and like save his life?
There was no saving his life. It was not possible. He didn't take as many painkillers as he could have, so that he could try to be lucid enough to describe what was happening. Like he knew he was going to die, so he just tried to make himself of scientific value, which is hardcore or crazy, depending on how you look at it. All right, let's do attendance after that gruesome introduction. Kingston?
Did you get me?
Yep, I got you. Trevor?
Here.
Great. Parker?
Here.
Okay. Chase?
Right here.
Okay. Karina?
I'm here.
Okay. Darren?
Here.
Okay. Brooke?
Here.
I heard you already. Zach is here. Pine's here. Porter?
Here.
Okay. And Michael's here. Okay. So a few of you weren't at the lab yesterday. So I'm just going to make the same announcement. The lab class is a separate grade than this class. And there are a few of you who are missing lab reports. And that is the majority of your grade in that class. Some of it is that you said, hey, I'm uploading it, or you entered some text box information, but your lab report is just not attached to Moodle. So make sure you're looking at my feedback. Those of you who tried to submit something and had technical difficulties, I will still grade it. If you just didn't submit anything, make sure you don't miss any more because that's a huge part of your grade. But be checking the lab class, because a few of you are going to be struggling in that class because you're missing assignments. Okay. We're going to talk today about system engineering. And this important DOE required program. Everyone online, can you guys see the presentation?
Yes. Yeah.
Awesome. Okay. So we're going to talk about what system engineering is, why it's needed, and how it works. This is not a responsibility that you as operators will have. The cognizant system engineer is responsible for implementing this program per the DOE order. However, it is extremely important. As operators, you are going to be the system use experts. You're going to use these systems day in and day out. You're going to understand how they work. You're going to be very familiar with their particular idiosyncrasies. And so you have a very valuable role to the engineer, which is you actually use the system. And the engineer has an incredibly valuable role to you in that that is the person through whom you must go to get repairs or improvements or modifications to the systems you use. So as an operator, the system engineer for any of your systems that you are assigned to operate should become one of your best friends. They are one of the subject matter experts that are going to help you in your job. And there are certain things that per Department of Energy or Nuclear Regulatory Commission regulation, only they can authorize and do. You as an operator cannot actually change your systems, even though you might be the first person who recognizes a change or maintenance or modification needs to be done. You have to work with the engineer to do that process as part of our overall work control and system control processes we have at nuclear facilities. Okay, so what we're describing today is not necessarily going to be your job, but it's going to be the job of somebody who's going to interact very closely with you, and you need to understand why they have to do things this way. Okay? So the cognizant system engineer maintains overall cognizance of assigned systems. So this person is going to sign the drawings that tell you what the correct normal lineup of your system will be. They're going to know the current, upcoming, and long-term support needs. They're going to have a plan for major replacements. If it's something that requires the plant to be in an outage to do a replacement, that can't just happen at any time. That has to be coordinated with when the plant is actually going to be offline. Commercial nuclear reactors don't want to go offline more than they have to. A lot of experiment reactors don't want to have outages where they can't be performing experiments. There is some performance and money driver in the industry. So they're going to have a plan to fit each one of these replacement or maintenance needs into a scheduled outage or a time when that system is not needed. This is especially difficult if it's a safety system, because you might have to put in compensatory measures in order to take a safety system offline, which means that operators are going to have to do something that they're not used to doing to compensate for that system not being available, even in a shutdown mode sometimes, okay? They're also supposed to be the experts in these system interactions from their system to other related or nearby systems. So the design of the safety envelope around our reactor has to consider that various systems might interact in unexpected or unusual ways. The engineer is really supposed to be the expert in this, whereas you all as operators are supposed to be that system operation expert, right? So you give two different perspectives based on your familiarity with a given system, okay? They provide support for both operations and maintenance. The engineer determines if that system needs to be on a preventative, corrective, or predictive maintenance program. Have you guys heard those terms? Have those been defined in some of your classes?
Yes, a little bit.
Okay.
Predictive.
So preventative means that you do maintenance on a schedule before something actually needs to be fixed. So you're preventing a degradation from ever occurring by saying, okay, I know that this particular valve can operate 400 times before it starts having a binding issue. And so at 350 times of operation, we're going to replace it so we never get close to a binding issue. Corrective is, once something is broken, let's fix it. We're going to correct the deficiency. And predictive uses monitoring devices to say the current is fluctuating more across this pump, which means that it's starting to show signs of having suffered cavitation. Now that we can measure that actual need, we're going to put this in before, we're going to put the replacement in before the current gets to that. So we're using actual data to predict when we need to do a replacement to keep the system functioning, okay? So the engineer is going to decide which of these types of maintenance needs a system has, okay? They're going to design that maintenance schedule. They have to write and sign each one of the work orders. So if maintenance says this is how we need to perform this particular job, the engineer has to sign off on that being the method that's used. And they're also responsible for signing a system into or out of service. And all of this is required by the regulations. We are looking at DOE Order 420, Chapter 5. So we're looking at the DOE System Engineering Program because that order is free. NRC new regs are behind a paywall a lot of times, but it's very, very similar in the NRC world, okay? They also provide technical support to the management group and advocate for the system, improvements and replacements. This is something that operators will also do. Advocate to management for improvements and safety changes that you need. but the main person responsible for that by regulation is the cognizant system engineer. And so they're going to be they're going to have a little more authority when it comes to talking to management about the system, okay? They are essentially the system's technical expert. You're the, operator, you are that system operation expert. This is the system technical expert, okay? So, DOE uses 420.1c, facility safety. NRC uses ANSI and ANS standards, okay? So, everybody open up DOE order 421c, chapter 5. It's on the Moodle, or I said that you might want to have a printout of just chapter 5 for today. Okay, oops, let's put this up here. Okay. So, DOE order 421c, its objective is to establish facility and programmatic safety requirements for DOE and NNSA for nuclear safety design criteria, fire protection, criticality safety, natural phenomenon hazards, mitigation, and the cognizant system engineer program. So this order has 5 parts, all of which are designed to keep our facilities safe. So this is how we design them. This is how we protect against fire. This is how we protect against criticality. This is how we protect against earthquakes and hurricanes. And then this is the person who has to ensure all those systems stay protected. We're going to skip to chapter 5, even though all of the other components are important. We're just going to talk about cognizant system engineers. Let's see. Oops, I went too far. Chapter 4. Chapter 5. Starts on page 31 of the PDF, if you're looking at the PDF. Okay? So, we're going to designate cognizant system engineers who are responsible for maintaining overall cognizance of assigned systems, providing system engineering support for operations and maintenance, technical support of line management. Okay? Okay. In that document, it says that it's required for HAZCAT 1, 2, and 3 nuclear facilities. Do you guys see that? See that requirement?
Yes.
Okay. What is a HAZCAT 1, 2, or 3 nuclear facility? Does anybody know? That's a good thought, but we're in DOE right now, so none of these are going to be power reactors, right? We have all levels of experiment reactors, and actually, if you look, it says nuclear facilities, not just nuclear reactors. So that's a good thought for splitting them up, but it's not quite what we're going for. Who else has a guess?
Is it like split up between like 1, 2, and 3 is like, it's like where it's like enriched is like one of them, and then like 3 is like the actual reactor like facility, and then like 2 and 1 are like the other processes like up to the reactor?
That's actually pretty close, but not quite. But we'll go with that because that's really close. So hazard category 1, 2, and 3 can be all sorts of different facilities, but essentially how big of an accident they can have decides if they're 1, 2, or 3. HAZCAT 3 facilities are non-reactor nuclear facilities that do not require the same amount of protection as HAZCAT 1 and 2, but still require active safety systems. So right here, this bullet, active safety class or safety significant systems, structures, and components, SSCs, know that acronym, okay? What this is saying is that they're capable of producing enough radiation in an accident that is likely enough to occur that we have to have active systems that we employ to protect the public from a radiation dose. So that is how DOE defines their hazard category, is radiation dose to the public. Then they backtrack that and say, okay, we can't have above a certain dose. How do we ensure that we protect the public? Can we do it just passively? Can we just put some shielding there and it's done? No, we have to have an active system that's powered and activates. Okay, now that we have to have those active systems, we're now hazard category 1, 2, or 3. 3 will always be non-reactor nuclear facilities. 1 and 2 can be reactors. This will be category B reactors. And this will be category A reactors. The only DOE category A reactor is the advanced test reactor at INL. All the other reactors at INL are category B reactors. So the accident conditions are less significant. Yeah, Michael. INL has the advanced test reactor, the advanced test reactor critical, the treat reactor, and INRAD. And they're getting ready to build a new scale reactor and the Oklo micro reactor and the versatile test reactor. Hopefully, we hope, if all 3 of those do get done. They've had over 60 reactors on their property in their history. Okay. Chapter 5 establishes the requirements for the CSE at these facilities to ensure continued operational readiness. Why are we calling it operational readiness instead of safety? What does this operational readiness term mean? Anyone online have an idea why we're using the term operational readiness instead of talking about safety here?
Because the safety systems are like operational, and so they need to be operationally ready to work.
Exactly. We're already saying it's for safety class or safety significant, right? And safety class means it's protecting a scenario where radiation can get off-site, and safety significant means it's protecting where radiation could get out of the facility but on-site, okay? So we're assuring that our safety systems actually function, which means that this entire order is about safety, right? We have to make sure our safety systems work in order to protect what they're required to protect. So the entire purpose of a cognizant system engineer is to ensure the operational readiness of safety class and safety significant SSCs and HAZCAT 1, 2, or 3 DOE facilities. Okay? What kind of systems need to be enrolled in a system engineering program? Always you're going to see control rods. Even if you have some amazing reactor design and your control is passive, what you take credit for controlling the neutron reaction in the reactor is going to be a safety system that has to have a CSE. Active cooling systems, so primary pumps, sprayers, emergency makeup water, tanks. Important to life shielding may not be an obvious one. It's a passive system though, right? So it may seem like you should have it in a cognizant system engineering program, but you won't because this is passive, okay? The BWR accumulators that we talked about, that nitrogen bubble that sits on top to push the water out, that's passive. So even though this is a safety system and it's significant and important, it's a passive system. So you don't have to enroll this in a cognizant system engineer program. Based on the lab that you guys did yesterday and some of the reading that you did and the previous lectures, what are some other systems that need to be in a cognizant system engineering program? What are some of our other active safety systems?
Maybe the steam.
The steam separator and dryer?
Not a safety.
Probably not the separator and dryer, but that steam goes through that process and goes somewhere to take the heat away. And so your ultimate heat sink, where that heat is going with the steam, usually is a safety system. You usually have to have somewhere to put the heat in case that breaks down. So not quite the separator dryer, but where the heat is going on the steam, we do have to have a place for that. What else? Someone online. What's another one that you think might be necessary?
Having controls for the control rods that make them drop faster than just gravity.
Yep. So the control rod drive, in addition to the rod itself, I would agree. What about some of our radiation detectors? Do you think that having a lot of scrams and protective actions based on a minimum radiation level means that being able to detect that is a safety function?
Yes.
Yes, I would agree. Radiation detectors are usually always also in CSE programs. Criticality monitors are almost always assigned to a CSE program. What do you guys think about containment structure? So the building the reactor sits in that has to withstand a jet falling on it, is that in a CSE program?
Yes.
Brooke says yes, Michael says no. Why do you say no? You say yes? Okay. So this would actually fall into the category of it seems like it should, but they're not really required because the building passive. And we have a requirement that they're active systems. So once you build the building, per the design requirements and the safety requirements, it exists, right? You might have a requirement to check that it's not degrading periodically, right? That the concrete isn't starting to wear and crack, but it usually won't be in a cognizant system engineering program. However, we're going to find out as we talk about this that management of a facility can decide to put any system they want into a CSE program. So even if NRC or DOE doesn't require that type of system, management may decide this system is so important, so difficult to replace, and has regulatory requirements attached to it that are other than this, we're going to go ahead and put it in the program. Okay? So we talked about this acronym, safety SSCs. It stands for structures, systems, and components. Okay? This is basically everything you can find in your facility. It can be just a part of a system. It can be the overall structure. It can be the whole emergency cooling system. You can define what needs to go into the cognizant system engineering program very specifically. When you guys are looking at chapter 5 of this PDF, Do you guys see where it talks about graded approach? Right here on part 2. A graded approach must be used in applying the requirements of the CSE program. The program must be tailored to facility hazards and the systems relied upon, considering remaining lifetime, safety significance, and safety importance of the system. So what they're saying here, safety class protects the public. If you have a safety class system, it means that you have a maximum postulated accident that is capable of causing radiation release to the public, off-site, away from the workers, all the way to where the public are. So if INL had to have safety class systems, it's to protect Arco and Idaho Falls and Blackfoot and potentially Pocatello, right? That's where our off-site public is. Safety significant protects the local worker. So you no longer have an accident that is large enough to threaten the public, but you can affect your workers who you do need to protect as well, okay? Below that, we have important to safety. This protects a system, a safety class, or safety significant function. So this protects its own systems, or this is extremely costly or difficult SSC to replace, so it's given more care. It may not actually be accident prevention or mitigation to be important to safety. It could just be very difficult to replace, and so for the safety of being able to continue to function as a facility, we're going to protect it. Defense in depth is additional protection after our credited SSCs. So a safety credited system is either safety class or safety significant. NRC uses some slightly different language at most plants, but they have the same hierarchy. There's a system, I believe they call it safety related, protects the public. And then you have one locally that protects the worker, and then you have important, and then you have defense in depth, okay? It actually might be important to safety is their top one, and safety related is their second one, and then defense in depth. I forget for the NRC. But for DOE, this is the way they do it. So when they're saying graded approach, given that some of these are just additional protection and some of these actually protect the public, which do you think is the most important to have a good CSE program for? Safety significant? Okay. What about online? What do you think is the most important one to have enrolled in a cognizant system engineering program?
I'd probably say safety class.
I would also say safety class.
Safety class. So it is actually safety class because this is a bigger accident because it can reach off-site, right? So, you know, protecting the worker, I agree with Michael, this is extremely important. But we're saying that we don't have to have safety class systems because our accident doesn't get big enough to reach off-site. So those safety class systems are going to be the most significant. They're going to be given the most attention, the most money, and the most protection. Okay? I put in here the NRC definitions. So, but I made a typo. So this should be important to safety, and this is safety related. So I apologize for that typo. That first one should be important to safety. So these have to be relied upon to remain functional during design basis events, and these have an impact on safety. Okay. Design basis events are the types of accidents a nuclear reactor has to be designed to withstand. So if you build a reactor in California versus a reactor in Idaho, do you think that they have the same design basis earthquake that they have to withstand? No, because Idaho does not experience earthquakes like California does, right? So if we said you have to build a nuclear power plant that can withstand California earthquakes, and we never get California earthquakes, that's not a design basis event. That won't happen here. We do have to design for snow loading that California doesn't. We do have to design for sustained high winds that California doesn't. So each design basis event is for a particular facility in a particular location, the accidents that they have to be designed to withstand. Okay? Okay. Now, there is some inherent antagonism in the relationship with the CSE and the operator in most cases, because they might be the technical expert, they don't operate the system. And you are the system function expert, but you're not an engineer. So you're each going to have different perspectives on what is the most important thing with regards to that system, right? The engineer is going to want to ensure that that system stays lined up the way it needs to, that it is able to function in a certain amount of time, and they don't really care if the method they use to do that is easy to operate. They've met the requirements, and they've done so in a cost-effective and mechanically efficient way. But you as an operator, you don't want the dial for a valve that you have to turn daily to be underneath 3 pipes and in the back corner of the room, and you have to do some gymnastics to get at it to operate it, right? You want that pipe where you can, that valve where you can reach it and you can operate it and you can verify the lineup. So you might have some slightly opposed or differing objectives when it comes to the same system. Okay? Like we said, the most technically elegant solution or improvement may not be the most operationally feasible. So it's important that when you're working with the CSE who has cognizance over a system you're operating, that you guys understand the slight difference in your perspective for a system. The CSE should trust your expertise. You should be so familiar with how that system operates and its function that you should be able to give that engineer information that they don't know that's very valuable for them in their process. And they should rely on you as those functional system experts. And they should know that when they create rules to protect their system, they should have trust that the operators are going to understand where they're coming from and why those rules need to be followed, okay? Essentially, each of you is going to have knowledge of an aspect of the system that the other does not have expertise in, and you have to rely on this relationship to ensure that that system is operationally ready to perform its safety function, and that you as an operator are able to activate that safety function, okay? This is famously one of the areas that in the real workplace, there is unnecessary tension between operators and engineers. And as someone who is both an operator, an engineer, and a regulator, I can tell you that it leads to far more problems than is necessary. So know your role. You're the operator. You're not the engineer. That is in no way a put down. Be proud of the fact that you are here to be the functional experts of a system. But understand the engineer has different knowledge, different expectations, and a different role. And together is the best way to ensure that that system functions safely, efficiently, and reliably. And it's required that you do this by the regulations, okay? System engineering programs establish something that's called a configuration management program, okay? This ensures consistency among system requirements and performance. It provides a system for documenting important things about our system, like drawings, and it protects and maintains the physical configuration of the system, okay? Configuration management is going to have system design documentation. It's going to have regular records of system assessments, whether that's through operator round sheets and operator walkdowns or engineering walkdowns and engineering assessments. It's going to control maintenance. Maintenance techs can't just go start taking apart and replacing a pump because it's time to do so. Not only does the engineer have to put that system out of service, the operators have to authorize the start of that work on the system that they have responsibility for, okay? You also can't just replace certain parts of systems with a similar replacement because you decided it's similar. The engineer has to evaluate when you make a change that that change is actually going to still allow the system to perform as required. And occasionally you update a facility and you have a system that becomes obsolete. When you put in new radiation detectors, you may not need the old monitors, right? System engineers, operators, and maintenance have to follow DOE standards 1073, 2003 for your configuration management. The NRC has an ANSI ANS standard for configuration management. And that's what we're going to talk about in our next lecture. But I wanted to make sure to put it in here so you see how system engineering feeds into configuration management. And as we start talking about configuration management, that's where there's going to be a whole lot of rules and roles and responsibility for the operator. But if you don't understand that it's coming from the system engineering program, a lot of that good relationship between the operator and the engineer that ensures the system is most reliable and most able to function isn't accounted for. Does that make sense? Any questions? Okay. Anyone online? Any questions?
have experience with this, difficult situation or potential difficult situation between engineers and
I watched it happen a lot as a regulator because I would be there when the operators were talking about a system that they just couldn't get repaired. And then I would be there when the engineers were talking about how the operators' desired repair was not going to meet the requirements of some standard associated with the system. Sure, it'd be easier to operate and it might remove an issue they're having in the control room, but it wasn't going to be sufficient for all of the system interaction requirements that that system had down the line. And so a lot of it is just when you get focused on your individual area of responsibility and your individual area of interacting with the system. You get tired of the fact that you have to reset this alarm multiple times because there's a short here and you want to put in this different type of wiring. Well, that may not meet the requirements of some other requirement of the system down the line, right? So it was a lot of that. And also, as an engineer and having worked with the engineering group, I can very honestly say that engineers are often very arrogant and they always think they're right. And so it can be very difficult to explain to them if they have not been taught how to value an operator's input and perspective. It can be very difficult to tell them, well, your design might be technically elegant, but it's not operationally feasible, right? And so they have to go back and they have to start over because they didn't think about the operators actually using the system when they proposed a change or an improvement or a modification. So that's, as an engineer, I can say that that's pretty consistent among engineers. Yeah.
So when you're an operator, you're obviously controller. Is there other things outside of controller that you have to operate?
Yes. So one of the things I'm trying to do with this program actually is split into two tracks. There are control room operators, but then there's also auxiliary system operators or plant operators, sometimes they're called, who are essentially like nuclear engineering techs, right? So your control room operator, it's a very specific personality type. You have to be able to sit in place and watch a system without being distracted or bored. And as soon as that system deviates from its normal parameters, be able to very quickly respond and understand what the system is telling you without also missing any important information while you're sitting there expecting the system to operate normally. It's a very specific personality type, in my opinion. So that, that's our control room operator. A lot more operators are hired in nuclear facilities to be in charge of doing system walkdowns, actually causing a system to function, turning on the demineralizer or turning on some sort of backup cooling and working with maintaining the safety systems and their operation, even though they're not normally operated. Whenever there's an outage, you have to go operate those to make sure that they're, able to respond when you need them. So there's a lot of operators who won't sit in the control room, but will be out in the facility. And one of the things I want to do is have those folks who want that, who don't want to sit in a control room, but want to go through this program. We're going to give you a few more of Evan's mechanical classes, so you're a little bit better at actually operating those systems rather than thinking about the system interaction that's happening in the control room, because there are so many different types of nuclear facility operator. Does that answer your question? The auxiliary system operator, plant operator, facility operator, all of those terms are kind of used at different facilities to mean the same thing. Okay. Any other questions? Okay, I have one review question. Define SSC. Correct. And then online.
Structures, systems, components.
Exactly. What is safety class?
Protecting people
Like
for
public.
large.
Protecting the public. Yep. Safety significant is protecting the worker. Someone online. What is safety related? The NRC term.
Is that the safety of like the machines and like the operations?
It's the object has an impact on safety. Yep.
Okay, yeah.
And then important to safety. These are the ones that have to be remaining functional during a design basis event. Okay?
Yeah, operation.
Yeah. Alrighty. I will see you guys on Friday.
Thank you.